so we were in the middle of this example, right? So we had this linear graph here. We had done step 1, right? We had done the normal tree, primary variables, secondary variables, state variables, state input, output vectors, elemental equations, continuity, and compatibility equations. So now we have step 2. So I did end up in the second section, started labeling these with the numbers corresponding to the steps that were given. So my apologies, slightly different than your notes. So this 2a was to eliminate all secondary variables by substitution into the elemental equations of the continuity and compatibility equations. So essentially we need to rewrite the elemental equations again, but eliminating, what's up with this one? But eliminating the secondary variables. Fortunately, we've solved for all of these secondary variables in the continuity and compatibility equations already. So our substitution is just ready to go for us. So let's rewrite our table C, L, R1, R2. And we have dVC dt equals 1 over c. And then instead of IC, we're going to eliminate that secondary variable by substitution with this equation here. IC is equal to I R1 minus IL. The next equation is DIL dt equals 1 over L VL, right? 1 over L. And then instead of VL, we're going to substitute in negative VR2 plus VC. So we've used this equation. Now the two resistor elemental equations. So VR1 equals R. I'm going to eliminate VR1, so I need to solve for IR1, right? IR1 equals 1 over R1 times VR1, and VR1 is just VS from our compatibility equation, VS minus VC, so this guy right here. And in the last equation that we have, so VR2, we want to eliminate IR2, so we don't need to rearrange this one. VR2 equals R2 times IR2, which we can substitute in IL for. And we've eliminated all of our secondary variables. This part always goes like that, okay? It's always easy, just plug in, no problem. 2B is the part where things can get a little hairy, but we're gonna see what we can do. I don't have my notes on this one, so we're doing this live and in full color. So yes, let's see if we can eliminate the non-state and input variables. So our state variables are VC and IL, right? So those ones are good. We don't need to get rid of those. VS is an input, so that's good. We don't need to get rid of that. Everything else needs to go. So I see IR1 and VR2 as being the two variables remaining that we need to get rid of. Fortunately, these R1 and R2 equations are solved for them, and they're already expressed in terms of state variables. And this works out like, I don't know what percentage of the time, but some percentage of the time, these equations here, I always write the equations for the elemental equations for the energy storage elements on top. So the lower ones always end up being the ones you need to use to substitute and get rid of variables. Fortunately, we can just do that directly. So let's use these. So substitute R1 and R2 equations to eliminate IR1 and VR2. So once again, a warning, it doesn't always work out this nicely, but in this case, it works out pretty nicely. So our C and our L equations remain. We have dVC dt equals 1 over C times, instead of IR1, I'm going to plug in this expression, okay? 1 over R1 times Vs minus Vc. And then instead of IL, well, actually, I don't need to get rid of IL, right? IL is a state variable, so we're good. Now this equation has the following variables: Vc, Vs, Vc, and IL. Good. All stator inputs, right? So that equation's good to go. The second equation is di L dt equals 1 over L times, so negative VR2, we can substitute in this expression for VR2. So negative R2 IL plus VC, which is a state variable, so we don't need to get rid of that. And we are good to go. Now, I am going to rewrite this in a way that allows us to do the next step easily. So we're going to end up writing this in a sort of standard state equation form next. So I need to know the coefficient of each of these variables. So I'm going to actually going to distribute these quantities through and rewrite it in a way that looks a little bit uglier, but it's going to help us do the next step easily. So VC is actually the first state variable in the state vector, so I'm going to list it first. So we need to write the coefficient of VC, which is 1 over R1 C, and then there's a negative sign on it, right? So negative 1 over R1 C times VC. And then there's going to be an IL term, which just has, so negative 1 over C IL. And then the last term is an input, so 1 over R1 C is the coefficient, 1 over R1 C Vs. And this equation has a VC and an IL. Let's write the VC coefficient first. So it's 1 over L VC. And then the other term is negative R2 over L, right? IL. If I make a mistake in here, just let me know. Okay.
I don't think it's spotted. It's too early in the game.
Yeah. So we can do 2C, which is to write it in a standard form. Okay. So in standard form, we have our state vector, so the time derivative of our state vector, so I'll just shorthand, just do x dot, equals an A matrix we want to fill out, right? So let's go ahead and draw it in the right dimensions. It's going to be a what by what matrix.
1 by 2.
So our x vector over here is a 2 by 1, so it needs to, so remember the A matrix needs to multiply the state vector, which is a 2 by 1. I'm going to actually write out the state vector. So it's VCIL, right? So whatever this A matrix is, it needs to multiply a 2 by 1 to get a 2 by 1. So it needs to be a 2 by 2, right? Inner dimensions have to agree. And it has to end up with 2 on this side, and it needs to match the inner dimension of 2 on the other side. So it has to be a 2 by 2. Which it's always, so if n is the order of our system, the A matrix is always an n by n matrix. And it's a second order system, so it's always a 2 by 2. It's always square. Well, in this case, it's a 2 by 2. It's always square. So then we have plus the B matrix. So it has to add with this what will be a 2 by 1 vector. So it has to be ending up being a 2 by 1. So the first dimension has to be 2. And then it multiplies the input vector u, which is just a 1 by 1, right? Vs. Therefore, it has to be a 2 by what? 1. Exactly. So it needs to match that inner dimension of 1 there, and so it has to be 2 by 1. So essentially we just need to transcribe these equations, scalar equations, into this form. Always is going to look like this, so now we just need to fill in the blanks. So the first blank is VC, okay? So if you read off the top equation here, says dvc dt, which is the first value in x dot, is dvc dt, equals, and then the coefficient of VC, the coefficient of IL, because that's what the first equation will come out to be. This is a 2 by 2 multiplying a 2 by 1, and you do this row times the column to get the new value in that first entry of the vector that results from the product. So we need to do negative 1 over R1C in this first element. And then what's the next one? It multiplies IL. Negative 1 over C. Exactly. And then we have also summing with something times Vs. So what is that? 1 over R1C. Great. So we've got our first equation transcribed into the standard form. Now we just need to do the second equation. Second equation has, what's the VC coefficient? 1 over L. What's the IL coefficient? Negative R2 over L. And what is our VS coefficient? It's just 0, right? With no VS showing up in this equation. And that is like, so this is the state equation. We have done the bulk of what we needed to do. That was the hard part, getting to the state equation. But actually notice we took it step by step. Well, actually wasn't that hard. There was no one step that was super difficult. The one step that could have been difficult was 2b, but it turned out to be easy. And fortunately, on an exam, I'm not going to give you one that's an in-class exam. I can't expect you to do a whole lot of algebra. So it's going to be something pretty straightforward. That's just some substitution, and you're good. All right. So now we need to do 2D and 2E, which have to do with the output equation. And I'm just going to come over here. There's a blank spot over here. And let's do what did I call it? E? No. D and E. So 2D is to write the output in terms of state and the outputs in terms of state and input variables. So our outputs, we have 3 outputs, IL, IS, and VR2. So I'm just going to list them here. IL, IS, and VR2. So we just need to write these in terms of state variables and inputs first. So IL, how would we write IL in terms of a state variable or an input? It already is a state variable, so we're good. IL equals IL. All right, so that was a gimme, right? I know, the gimmes are the ones that always freak people out. And then the second one is IS, which is not a state variable, it's not an input. So it's the current coming from the source. We want to know what that current is, apparently. That's something we're interested in. So we need to write that in terms of state variables and inputs. We do know, for instance, from looking at this, that IS is equal to IR1, right? Well, actually, IS is equal to negative IR1. So that could be our first step. We could say IS is equal to negative IR1. That's also not a state variable, and it's not an input variable. So we need to find some expression for IR1 that relates it to a state and an input. So if I look through these equations here, I see, well,
Well, IR1 is equal to IC plus IL.
so there's something promising. So let's try that. Let's use this continuity equation. So I is equal to IC plus IL, right? Now IL is a state variable, so that's good.
But IC is not.
But IC is not. So let's see. And I haven't finished this problem yet, so I might have given you guys something that was a little harder than I was meaning to. But let's see.
Harder for us or harder for you?
Don't we already have that IR1 is equal to 1 over R1 and VS minus VC?
Right here.
Yeah.
Very good.
We do. Why don't we just skip to that?
Yeah.
Just
Good call. I didn't read it.
Boom.
Stuff.
so occasionally you'll end up with one that has the derivative of an input in it, or a derivative of a state variable. That is sort of an edge case that I'm just not going to talk too much about. The book does deal with that, and you can go into the greater detail there. It is an issue, but fortunately, we can get out of this conundrum with this equation here. So IR1 VS minus VC. So instead of going to this, let's do equals negative
1 over R1 times quantity VS minus VC.
VS minus VC. Excellent. And this is in terms of a state variable and an input variable. So, haha, we're good. Now, let us rewrite this in terms of, well, with each of the coefficients written out explicitly, which kind of helps us do the next step, just like with the state equation. So we have 1 over R1 VC, and then we have no IL, and then we have negative 1 over R1 VS. All right. Good. Whew. That one was almost tricky. VR2. Oh, we already have one of these equations written like this. R2 times IL in terms of a state variable. So, whew, we're good. So we had IL times R2. So R2 IL. Okay, so those are our three outputs written in terms of state variables and inputs. So now you can write it in standard form. 2E y is equal to. We need to write it in terms of some matrix, so the C matrix, times x, which is still just VCIL. So if there are three outputs and there are two states, what do the dimensions need to be? So if there are three outputs, this first dimension has to be 3, right? If there are two states, what does the second dimension have to be? 2. Yeah. So this is a 3 by 2. And then with inputs, we have, once again, the first dimension has to be 3, the number of outputs. And we have one input, right? Just VS. So how many, or what's the second dimension of the D matrix? 1. Just to match the inner dimension, right? So the first equation is that IL is equal to IL. So IL is equal to 0 VC, 1 IL, and 0 VS, right? Bam. We just essentially selected out IL. The second output is 1 over R1 VC, so 1 over R1 VC. minus 1 over R1 VS. So there's no IL in there. And then there's a minus 1 over R1 in the VS term. And then finally, we have our VR2, which has 0 VC, R2 IL, and then 0 VS. And my friends, we have arrived at a state space model, which is the x dot equals ax plus bu, and our y equals cx plus du. This is our C matrix, this is our D matrix, and then back over here, we didn't write it, but this was our A matrix, and this was our B matrix. So once we've got A, B, C, D, we have a state space model, if it's a linear system.
Go back to that last slide.
Yeah. Cool. Alrighty, so that is the end of this lecture. I'm going to switch over to the other one, and we're going to power through another example. Okay?